It's lovely to have you, Ken and Ryan. So I'll give a quick introduction to Ken and Ryan. So this is a dual presentation with Ken Goldberg, UC Berkeley. Ken is the WWII Floyd Distinguished Chair of Engineering at UC Berkeley and Chief Scientist of Ambi Robotics. He's also Professor of Industrial Engineering and Operations Research at UC Berkeley, Chair of the Berkeley AI Research Lab, and Director of CITRIS People and Robots Initiative. He is co-founder and editor-in-chief emeritus of the IEEE Transactions on Automation Science and Engineering, as well as he leads the robotics and automation grasping, manipulation, and learning for applications in warehouses, industry, home, agriculture, and robot-assisted surgery. And his PhD student, Ryan, is a third-year PhD student in electrical engineering and computer science department at UC Berkeley. His work is focused on the interaction of robotics and artificial intelligence, specifically on the development of algorithms for interactive learning and execution, where control is shared intelligently between learning robots and their human supervisors. So thank you so much for both of you. Over to you.
Okay. Bonjour, Damon and Liz. Merci de nous avoir invités. We are pleased to be here this morning to talk with you guys about human-machine collaboration. And we'll start by noting that when you have two or more people who work together to solve a problem, we call this collective intelligence. So what Ryan and I would like to do today is share some recent ideas about how this can be extended to robots. So in the next slide, we'll talk. I want to reference the history of robotics. Can you advance the slide there? Yeah, thank you, Ryan. So the word robot itself, as I think most people here know, was coined in 1920 by the playwright Karel Čapek. And the play, R.U.R, Rossum's Universal Robots, was actually quite successful. It played all around the world. And in the next slide, the idea was that you had many robots who are robot workers who were oppressed and were joined forces to rebel against the human human directors of the lab. And this was an early example of where the very first robots were working together. There was a sense of collaboration or collective intelligence among the robots. So in the next slide, I want to note that actually the first real robots were also collaborative in the sense that they always had a human working behind the scenes. So they were what we call tele-robots. And I think it's important to make that distinction between a robot and a telerobot. The telerobot is not autonomous. It has a humans driving it. And this goes all the way back to actually the 1898 when Nikola Tesla introduced the first radio-controlled robot boat in Madison Square Garden. And so even before the word robot was around, but then during the 40s, 50s, and 60s, there were a lot of advances. And some of this started with robots that were just mechanically teleoperated. And that was done, as you can see in that top figure, to be able to manipulate radioactive materials. But then that was extended quickly to exploration and being able to control telerobots in dangerous places. So this is where we started to see bomb disposal robots. We see robots going into mines and being used in autonomous, telerobot, air vehicles, water vehicles, and also in space. So there's a steady stream of research on this, and it continues to this day. Next slide. So one thing I want to notice is there's an interesting turning point that happened about 30 years ago when Tim Berners-Lee developed the World Wide Web. And at that time, I was an undergraduate student in I was a professor at Freudian slip there. I was a professor at USC, and my students actually came to me and said they wanted me to see this new thing, and we got very excited because we had a lab, we had robots in the lab, and we wanted to try out the World Wide Web in this context. All right, so we built a robot in we used an industrial robot arm, and we built a planter where we could have real plants living in this garden, and we installed the arm around in the center so that people could visit this garden over the World Wide Web. So David knows this. This was an art project that was online for 9 years. It provided an interface for the early version of the World Wide Web, the Mosaic browser, so people could go in and view the garden by clicking. On the left is an overhead view of the robot's workspace, and the camera was at the end of the robot. So if you clicked on different points, the robot would move and show you what was underneath. You could also water the garden, help us water the garden. And if you go to the next slide, you'll see that the system was able to not only water, but also plant seeds. So it was not autonomous because there's always a human essentially making the commands. But what we felt was interesting was the idea that there were many humans working together. There was this example of collective intelligence, and they were working to build this robot. Oh, excuse me a second. There's some strange music playing. Very odd. Okay. There's some kind of strange intelligence in this room. So, but what happened with this robot? Oh, I'm sorry. Hold on one sec. I must have said Alexa in there somehow, but Alexa turned on. Okay, so next slide. What we were interested in was, next slide after that, Ryan. This philosophical question that came up there in the context of whether or not the robot and the garden were real. And I don't want to get us off track. That was not the question we want to talk about today. But became an interesting philosophical question for us is what was the distinction, or what is the distinction between virtual reality and distal reality? And this question is I think even more relevant today as computers have advanced and technology has advanced, that the simulation is so good, and that it's very hard to distinguish between something that's virtual, fictional, versus something that may be distal, where it's a real environment but just far spatially. And this is really the essential problem of deep fakes in an early version. So next slide. We extended this because we were so inspired by the response. We extended this to something that we call the tele-actor. And here, instead of the robot, we replaced the robot with a human. And this was deliberately, we wanted to consider that human would be an actor, ideally even like a performer, because we wanted someone who was very gregarious and who enjoyed interaction with people and environments. And the key there, though, was that there'd be many teledirectors out online who are able to essentially look through the eyes of the teleactor as he or she explored an interesting environment, like, let's say, backstage at the Academy Awards or on the sidelines at the World Cup. So there'd be one teleactor walking around, but many people essentially looking through the eyes and making suggestions. In the next slide, we show how that worked. It was the collaboration there was the teledirectors would see a screen like this, and they could click with just to indicate various points in the scene with notes, making suggestions to the teleactor. And we did some research on how this interface might work, how the teledirectors would interact among themselves, and also how to summarize the information in an efficient way for the teleactor to be able to digest it and move smoothly through the environment. So we applied this to a number of environments, and we also explored how it could be used for teaching. So one was on the left, you might be in a museum, and again, you have a classroom of students who can't get to such a museum. It might be located far away. And so they can explore the museum by having the teleactor move around, and then they decide where to go. You could also imagine students who want to go into a clean room, which isn't normally possible for obvious reasons. So here you would have, again, the person explaining, and then the students actively getting involved by asking questions or voting on options, like opening this furnace. And then it could even be used, obviously, for the interface is pretty general, because you could ask simple queries and evaluate student understanding. So next slide. That was our foray into, and we're still interested in this idea of collective intelligence with robots. But I have to say that the entire field has consistently persisted with this idea, this image of the robot as an individual machine that is working in isolation and carrying all of its computer power and memory, everything, to be self-contained. And so this is an evolution of different humanoid robots over time. There's obviously been quite a bit of work since then, but the idea here is that these robots are fully autonomous and they have no real essential need to interact with others. Next slide. Now, there's been another trend which we're excited about, is cloud robotics, and that is where robots are increasingly in locations where they're able to connect to the internet and be able to work with remote data centers or remote robots to collectively share experiences and to learn specifically over time. So the idea is that robots can be located in many different environments, like many different homes, and they'll be able to upload data, examples of interactions that they have that could be used collectively to improve performance for the collective over time. So the next slide shows you that this has been accelerated by the major developments in deep learning, and that over the past decade has really accelerated because the key aspect of deep learning is the need to have vast amounts of data, of examples. So next slide, the one other major development that we're seeing, obviously, in the last 3 years has been the pandemic, and that has affected the field of robotics in the following way. If you go to the next slide, there's been a huge proliferation of telerobots, and it's because of the telerobots are very capable of working, they're much less contagious, or capable of being contagious. And so the telerobots have been already under development for things like telesurgery, but that has increased. And also drones have really been a huge success story in the field of robotics. Again, those are teleoperated. Next slide. And this is also there's a renewed interest in this for the home. Amazon introduced the Astro robot, which is, again, a telerobot that's operated by remote control. And this is very relevant to the developments in autonomous driving. So Waymo, branch of Google, introduced autonomous taxis in San Francisco recently, and the taxis they're only operating at night and only in very certain areas of San Francisco. And I should also mention that the dirty little secret there is that they only make right turns. So if you want to get from point A to point B, it usually takes twice as long as normal. But one of the features is that they do occasionally get stuck. And so as you'll see in the next slide, there's a human operator standing by. And this is interesting. You have a human who is basically can be alerted and called in when the robot encounters a situation it can't get out of. And so this is being adopted, we believe, by all the self-driving car companies, that they make use of this as a fail-safe, as a fallback. Next slide. The but we want to also emphasize that robots today in so many need is very prevalent because robots are just not as reliable as we would like. And there's many, this is just four of many cases of robot failure modes. Next slide, you'll see that but robots are being used increasingly in many remote applications, in many applications. And so we need methods that are able to manage the trade-off between robots acting autonomously and robots under tele-robot human control. Next slide. So this is showing you that this this trend of human in the loop is very prevalent. And as you see in these examples here, it's also Amazon is using something similar for robots in its warehouse. Next slide. And I like this quote from Elon reasons lately, but he originally started to build the factories for Tesla cars entirely autonomous. He wanted no humans in them. But after a year, 2 years of really struggling, he relented on that, and he actually admitted making a mistake here. So it was a great moment, and as you can see, it was right on Twitter. He said excessive automation at Tesla was a mistake. Humans are underrated. So we agree with that. Next slide. And so I'm going to turn things over to Ryan, who's going to talk about some really exciting new research that he's been developing on how this trend that we see can be applied very specifically to a problem in imitation learning. Okay, Ryan, over to you.
Okay, great. Thank you, Professor. So first, I want to talk about imitation learning. And imitation learning is this idea that has obvious relations to human intelligence, where we often learn from examples, whether that be from our teachers, parents, mentors, even videos on the internet, as this baby that's imitating Rocky. But when we try to apply this to robotics, what often happens is we get this phenomenon that we call a distribution shift. And the reason for this is that when the human is controlling the robot as a tele-robot, and the robot tries to imitate what it's seen the human do, there's a little bit of approximation error every time that it tries to imitate the human, and that approximation error compounds over time. So you can see that the trajectory eventually deviates from the one that the human had, and the robot visits states that the human never had, and then it has no reference behavior to imitate. And one reason we think that this is the issue is that, or one cause here is that we tend to think of human control and robot control as a binary bit that you kind of like switch, right? So something's either a tele-robot or a robot. It's either autonomous or it's fully tele-operated. But really, it's not the case here, right? Really, there's a spectrum of human control and robot control, and one end of the spectrum it's completely human control, and the other end is completely robot controlled. But in the middle, there could exist all kinds of autonomy solutions, and here we could call this perhaps supervised autonomy, where the robots are as autonomous as they can be, but when they need help for whatever reason, a human can step in and operate it as a tele-robot, and can call this paradigm supervised autonomy. And that's the trend that we see in all these companies like Waymo, Amazon, etc., for logistics and self-driving automation. Now, a couple of nice properties of supervised autonomy. One is that it can approach more robot autonomy over time, continuously, rather than trying to get there all at once, because the robots can always learn from their own mistakes. And the other nice property is that if we're clever about how we allocate an individual human's attention, then a single human could be allocated to multiple robots, right? Say each robot is 90% robot control and 10% human control, then one human should be able to monitor 10 robots if that in the ideal case. So in the literature, we call these algorithms interactive imitation learning. And the idea here is that there's some switching function you can call pi that determines at each stage should the human be in control or the robot be in control. And there's a popular algorithm called dataset aggregation, or DAGR, in 2011, which kind of pioneered this idea. And what happens is that you intermittently cede control while the robot is doing its task and give control to the human. That's why this one makes it interactive. And what this allows you to do is it lets the robot see how to do these little recovery behaviors from the states that it actually visited, and actually return to the states where it knows what it's doing because it's seen a lot of human data. And the central question here, of course, is how do we choose pi, right? How do we determine what is the switching function? And there's been a lot of work recently in this area. People are very excited about this now because it's not obvious how to do this, and it's an open problem. And there's been a lot of great work in this area. And one way that people think about it is called human-gated. And human-gated, the idea is that the human is the one that is going to determine pi. It's going to watch the robot continuously do its task, and then it will decide, oh, it needs help here. I'll step in, take over control, and then I'll give it back control when I think it's okay. And this often works very well, and it's very intuitive. But the main drawback is that it's not scalable. So if you have a lot of robots that a single human must operate, or a lot of robots per human, or maybe even just a really long period of time, this human is going to get either tired or overwhelmed by monitoring so many robots at the same time, and inevitably make some kind of mistakes. So the alternative to this family of algorithms is called robot-gated. And as the name suggests, now the robot is the one that is determining autonomously that it needs help for whatever reason. And that, again, leads us to the central question: when should the robot ask for help? So our answer to this was something that we called Thrifty Dagger. And Thrifty Dagger was a paper that we presented at the Conference on Robot Learning in London last year. And the idea is this. So think of an autonomous car driving in various conditions. So say it's a sunny day and it's just on a highway. Then this is a case that is neither novel nor risky. And what I mean by this is that novelty, we'll say, is some new situation compared to all the data you've seen before. While riskiness in this case is, are you going to get into an accident? And if you've had a lot of data on the highway in sunny conditions, then this is neither novel nor risky because you've seen it before and you're probably not going to crash. However, if you're driving on snow for the first time, then this is both novel for your system and also risky because you might careen off and hit a tree or something like that. And our insight in this work is that often we think of these two terms as the same for robots, but really they're off diagonal terms, right? So there are states that are novel but not risky. For example, like a wide open dirt road. Maybe you haven't seen it before, but there's nothing to crash into. And there are also states that are risky but not novel. So say you're driving a tight cliff, even if you've done it before, maybe you don't trust the system to get that perfectly right. Otherwise, the consequences are very severe. So a bit of the technicalities of how we did this. For novelty estimation, we used a technique called ensembling, which essentially trains several neural networks and measures their disagreement as a measure of uncertainty. And for risk, wouldn't worry about the math here, but we proposed this novel risk metric that uses reinforcement learning to essentially estimate how likely is it that I will complete the task from this state. And to put it together, Thrifty Dagger simply, at a state, if the robot is in control, if it is sufficiently novel or sufficiently risky, it'll switch over to human control. And human control, it will only give control back to the robot if the state is neither novel nor risky, from which the robot should be able to handle it, at least for a while. So among other experiments, one of the experiments we did was a user study of controlling 3 different robots. And the humans are performing this concentration game of like matching cards. And at the same time, these 3 simulated robots would ask for their help, and they would have to help them when they asked for help. And we found that compared to robot-gated algorithms, compared to a human-gated algorithm, Thrifty Dagger's criteria requested less burden on the human and also enabled higher robot task performance. So they were able to complete the task more successfully, and surprisingly enabled higher human performance. So even the humans were able to get further along in their game. And the big takeaway here is that robot gated help can be as good as human gated help. And so next we think about applying this to a more collective intelligence way, where we have a fleet of robots, and we really concentrate on this fleet idea. So I'm sure many of you have heard of the large models that are making the headlines these days, like DALL-E 2, GPT-3, Imagen, and so on. And they work by essentially scraping the entire internet and doing large-scale supervised learning. And here we're interested in large-scale supervised robots. And 4 building blocks we can say that it's on-demand supervision. That's the robot gated, like we said. Fleet supervision. So there's a lot of robots and a few humans that are controlling them. There's continual learning. So the robots are always learning from their own mistakes, sharing their experience with the other robots in the fleet. And we want to use the internet, which of course has a history all the way back to the Telegarden, which we talked about, but these days is very low latency, very reliable, so that the humans don't even have to be there physically in order to control these robots. So Fleet Dagger is brand new work that we'll be presenting in a couple of weeks in New Zealand. And we propose this paradigm called interactive fleet learning, or IFL, where there's a remote pool of humans and there's a larger, actually much larger robot fleet. And there's some Omega, this robot gated allocation policy that we want to learn, which is essentially, we want to figure out how to assign these humans to these robots. And this was the first formalism for interactive learning with multiple humans and multiple robots. So to get into the math briefly, Omega is trying to find a mapping between the state of all your robots and their policy to the assignment matrix of which human is assigned to which robot at any given time. And the objective we care about is return on human effort. This is a metric we devised, ROHE, which is essentially the ratio of how good are the robots at their task to how much human effort was required to get there. We also released a benchmark as part of this project, which was built on NVIDIA Isaac Gym, which is new software that came out last year that does end-to-end GPU acceleration. So it allows you to simulate hundreds or even thousands of learning robots on a single GPU. In simulation experiments, we developed a new IFL, interactive fleet learning algorithm, compared it to other algorithms, and found that it was more successful with regards to various metrics on a fleet of 100 robots. And physical experiments, we had to get a little more creative about how to get a robot fleet with academic lab resources. And we turned these 2 ABB Yumi robots into 4 robots, where each arm is acting as its own robot. And there were 2 humans available on the internet to take over while it did this image-based block pushing task. And we observed similar results here as well. And quickly, some dirty laundry limitations of this. We had several modeling assumptions, such as the humans had to be homogeneous and the robots are all independent and not acting as a swarm in the same environment. And these are some interesting directions for future work. Okay, I'm going to hand it back to Professor Goldberg to close it up.
Great job, Ryan. Thank you. So we've been thinking about this in using the term complementarity to talk about this interaction between the human, or the relationship between humans and the machine, robots in this case. Next slide. It's really there's been a lot of fear about robots essentially taking over jobs. In particular, you see this everywhere in the news to this day. But in the next slide, we really think that the future is going to be a combination of artificial intelligence with intelligence amplification. So the 2 aspects are complementary, and they really work together. In other words, enhancing machines, but also using machines to enhance human performance. So in the next slide, we show that this is really building on the recognition that there's complementary skills that machines are actually, no one denies that they're superior for calculations, precision, and objectivity, but what they're very far from, and we can discuss this, but I believe they're still very far from understanding and empathy, and in robotics, dexterity. Robots are still incredibly clumsy. Next slide. So we see this as a symbiosis, and where, you know, this is an ancient reference for some of you. It's way before Ryan's time, but you may recognize these two gentlemen from Star Trek, and what they're. I like to use them as an illustration of this because, you know, Spock was like a robot. It was all about logic and rationality, and Captain Kirk was all about empathy and human heart and subjectivity. So the two of them, the beauty is that they work together so well, and so they were able to tackle these major challenges. So I think that is actually the promising outcome that I would love to talk more about. And I want to say that I think that this is actually an increasing trend, and we're seeing this, and we'll be seeing more of this in the coming decade. So last slide is. So we did a study really briefly about with a number of leaders, including Tony Blair, who basically said AI is going to help us do the things that we were uniquely meant to do. And that is this higher level kind of creative thinking. And the next slide says that, I love this next slide, that this quote says, AI is not about replacing the human with a robot, but it's really about taking the robot out of the human. And by that, Diego Cohen basically means that we want to take away the drudgery and the repetitive aspects of jobs and allow humans to be able to focus on those more novel and intriguing aspects of work. Next slide. So that's it. Okay, great. So we're we're happy to talk and entertain any questions that you might have. Thank you very much.
Thanks. Thanks, Ken and Ryan. We'll open the floor for any questions.
And for those of you on Zoom, if you want to ask a question, you can use raise hand or put your question in the chat. I'll be monitoring.
Yes. Maybe when I just come in now.
So thank you both for a very interesting talk. And I think I agree very much with your approach on combining the robot and the human and both strengths. What I understood from your examples is that the two approaches that you explored was either the human asked the robot for help or the robot asked the human for help. And then the question becomes who takes the initiative. But still, it is some kind of real-time intervention that you were talking about. And at some moments, maybe what humans do is also they control prior to the execution. So they make a plan together, and then the robot or the team partner goes off and does something for, I don't know, half an hour, and then comes back, and there will be this debrief, and they talk about how it went, and then the next cycle, maybe they do better. So, and I think that's also a very important direction to go when it comes to robot-machine interaction, to shift the control more towards some kind of prior control, and let the robot alone for, you know, a while. Mm-hmm. Have you done have you done the research on that? Yeah.
No, I fully agree with you. So I think what you're referencing is, and yeah, that is a limitation, that these controls have to be real time. And, you know, one issue you could run into there is, you know, maybe there's a little bit of latency and situational awareness where the human has to figure out what's going on right away. But I think what you're referencing is a larger issue in AI where there's this popular book called Thinking Fast and Slow, where it references like the two parts of the human brain, the fast part and the slow part, where the system one is making the unconscious reactive decisions really quickly, and system 2 is the methodical, conscious, like logical, slow planner. And there's been a lot of work in system 1 kind of approaches. So that's what neural nets are really good at, is learning from data to just do that response right away, and less focus on system 2, which I guess deep learning as current state isn't as good at. So I think there's an interesting question there of how I think task and motion planning is a field that is going more into system 2. But it would be interesting, for example, for the human to set high level objectives and the robot to do the low level in that case. And I think there's some interesting works there as well.
Yeah.
Mhm.
Okay, thank you.
If I can add, I really like the question, and I think you're right about the role the human is in these situations is setting up the environment, right, and choosing the task. So the task that you see here with the pushing of blocks is actually we spent a lot of time. Oh, we can stop the screen share. Okay, thanks, Peter. The task of pushing those blocks, actually, Ryan spent a huge amount of time thinking about that and crafting it, because we wanted a task that essentially could operate in a self-supervised way over long duration. And so it had to be a task that could essentially be doesn't need human intervention every cycle. So what he does, just to get a little more detail there, is that at every point the system automatically selects a point in that grid, and the robot has to push the block to that point, and then it generates a new point. So this can basically run for hours and hours on its own, and occasionally it gets stuck, and that's where the human comes in. But it's exactly as you said, it was a very careful crafting of a problem like that was well matched to the algorithm. So I think you're exactly right. I like what also Ryan said about system 1, system 2 thinking, that that's a nice way of thinking about the complementarity. The idea is that they don't have to be real time, that in some sense you could have a sequential process. And what we like to think of is that we get to a point where these robots could run for hours or days without human involved, and maybe batch up some examples that they can self-recover, but they could batch up failure modes that the human could come in and look at, say, once a week. So there's other interaction models for interactive imitation learning that we haven't explored yet, but it's very similar to, in a way, how human groups interact. And so they're not always doing everything in real time. Sometimes there's long delays between the interactions.
Yes. We have a few more questions coming.
Okay.
Thanks for the presentation, Ken and Ryan. That was very interesting. My question is around that imitation learning, because I think on the graph when you showed earlier, there's kind of human kind of like straight here where the robot or the machines kind of deviate to another chart, and you trying to bring it back into the, what humans said. But what if through that learning, like through imitating and learning as it goes, the robot kind of prediction or the direction that they're going, actually the improvement, which is probably like a better way that human didn't see before. Like, is that possible, or is that kind of the human has to be kind of the ultimate goal or decision making? Or what your thoughts on that? Thank you.
Yeah, that's an excellent question, and that's actually a limitation of all imitation learning algorithms, which is that if you're imitating something, you're assuming that that thing is what you want. And often humans aren't the best. Of course, humans are suboptimal in their own ways. And especially when controlling a tele-robot, if there's a lot of degrees of freedom or something, it might be really hard to do that as efficiently as possible. So the other family of algorithms that a lot of people at Berkeley and elsewhere are interested in is reinforcement learning, where the robots learn from trial and error. So here there's some kind of reward function or cost function, and the robots just try a bunch of things and they see what leads to higher reward. So a particularly interesting direction is how can we combine these two directions, because a big problem with reinforcement learning is it takes a very long time to just randomly chance your way into something as good as the human would have done over a long search process. But if we could maybe start with imitation learning and refine it with reinforcement learning, or maybe some way of like combining those two modes, then as you said, we could outperform the human. And that's an interesting direction for future work as well.
Thank you.
That's great. And actually, I appreciate that. I think that, in one case, you're absolutely right, where there could be some serendipitous motion that
Sorry,
the robot performs that actually.
We are losing you a bit.
Okay, so I'll stop. No, go ahead.
No, try again.
All I was going to say is that I think I like this point very much, because it. Thank you for asking that, because I think it is the idea that there could be a serendipitous moment where the robot lucks onto improvement over the human behavior, and we want to set the system up to be able to capture that and build on that.
Thanks. Do we have any online questions?
We have no online questions at the moment.
Anyone else who wanna? So yes, Dylan.
Everyone, hi Ken, awesome talk. Yeah, I really love your telegarden artwork. It's very beautiful. But yeah, I was curious, this utopia that you talk about, this future with AI and humans both doing the best thing that we can. It seems very. I'll just play the Kirk for a moment. It seems very like up here. So it's not. We're not using our bodies anymore. We're just like processing machines. And I see that the things that you work with normally have some kind of physical embodiment, but it doesn't really seem like it's taking advantage of that. I'm wondering if you could say something about that.
Okay, great point. No, I think you're so right about that. I think that so much of this the interaction has been in the form of interaction of the internet of essentially just data sets that might be search keywords and other things. I do think that it's moving into the aspect of embodiment in the sense of, let's say, computer vision, learning to recognize objects, and there's a spatial, three-dimensional, very much embodied aspect of that. But I think you're particularly right about things like grasping and physical interactions with the world. That has been, the progress there has been much slower. And so that's why in our lab, we focus on robots and physical manipulation. And the challenges of just something as simple and intuitive for humans as grasping is still very prohibitive for robots. We've made progress, but there's still a huge amount to go. And so that's where this collaboration in terms of embodiment, I believe, is very important, because this comes back to some of the work of Hubert Dreyfus and others, in looking early on about some of the critiques of AI, that it was all it was logic based or text based, that it really is important to have an embodied interactions with the world, to not only for being able to do things robotically, but also really to understand and ground language. So many of the metaphors and other things that we use are based on physical metaphors. So I think this is an area that really is ripe for lots of research. I'm actually really curious what the group at the workshop is thinking about in this regard. Ryan mentioned the large language models and all these projects that are showing incredibly interesting results today. Liz included that beautiful illustration during the tea break of DALL-E's result. I mean, these are fascinating, and I think that trying to put these together with robotics is a big, really interesting challenge right now. Ryan, do you have some thoughts on that?
Yeah, well, there's a few works, or actually a lot of people are excited about this. So one of the papers that inspired this was called SayCan. That was a paper from Google, and their idea was like, okay, can we take some of the knowledge that's contained in these large language models and somehow apply it to physical manipulation in the real world? And their approach was, let's kind of get long horizon text directions from this large language model and then convert that into the actual robot skills that we care about, which you learn through imitation learning or reinforcement learning or something like that. So you'd say, I spilled my Coke, how can you help? And then the large language model would say, oh, I would go get a sponge and, pick it up and go clean it up or something. And then you could take each of those steps into a concrete robot skill that you execute in the world. And now there's a lot of people that are trying to do similarly inspired works.
Mm-hmm. Good. And I just saw that Peter mentioned something in the chat about Gordon Pask and conversation theory. And so what I did was look that up right now on the internet. So and it's very interesting. I don't know much about it, but I will certainly follow up on that. I think that the idea of having conversation back and forth, that is a fundamental way that people learn. And I like that very much. I think there's a very new result that was just on the reported, I saw today from OpenAI, where they're pairing large language model with a Google search engine, and the two, being able to use the Google to evaluate the quality, the truth of statements, having the system do that on its own is a form of conversation. I think that's very interesting, has a great amount of potential. And how can we bring that into the realm of robotics is a nice question I haven't thought about before.
Got it.
Again, how are you doing?
Good.
So I kind of want to ask about, kind of tie together a few things. One of them is the discussion here that to me sounds a lot about simulation to reality, sim to real. Like how do you see the sort of achievements and challenges in sim to real? There's recently this work of having robots walk around Minecraft to learn about the real world and supposedly be able to solve real world problems because of that. And then that ties into all the stuff in your background, which is guitars and sculpture and a painting, and it looks like a handcrafted, so all of your background belies your love for craft and the tangible training and practice that goes into that, and whether you think the robot could just learn this from data and be able to achieve that craft. So.
Guy, you I love your questions. So brilliant. All right, Guy, I'm a huge fan of Guy Hoffman, and you always bring a bit of art to your questions and all of your research, and I really admire that. And I appreciate you recognizing the things in the background here. What I think that this idea of artistic exploration is important, and is something that I think is really open for in this field. I think that DALL-E, as I mentioned, is generating these creative. Now, there's such an interesting question we can have about whether there is creativity coming out of DALL-E. My own feeling is that it's a beautiful example of this complementarity, because it basically helps people, like almost all of us, including myself, who are not particularly great at drawing or painting, but you can generate images and you can start to evolve them. And this is the key that I want to emphasize. Hold on one second. So one thing is that I just recently saw a painter giving a talk about how he's using DALL-E to design paintings and sculptures. And it's a very evolutionary conversational approach, namely that he suggests things. DALL-E just suggests a number of results, then he zeroes in on certain, chooses certain outcomes, then continues to shape them. And he's using stable diffusion, which has that capability to evolve the images. And that is really interesting. So I think this idea of, again, complementarity in the idea of designing an image, an original artwork, a sculpture, is fascinating. And I have to say, I think it's opening up a new chapter in human creativity. And I'm very excited. I don't see it as taking over. I don't think this is going to eliminate artists by any means. I think it's going to open up the door to many more people taking on artistic challenges. And I think I'm very excited about that. Ryan, do you want to add anything to that?
Just briefly, I think Guy mentioned sim to real and how it can be applied to things like manipulation. And I've also been very skeptical that simulation will ever, get the contact mechanics and friction and everything just right. But there's an interesting recent work that surprised me, at least. So I put a link in the chat where NVIDIA did cube manipulation with a robot hand recently and got quite good results there. And then there's also this interesting idea that our lab has been, and other labs have been interested in, called real to sim to real, where we tune the simulation parameters with real world observations. And there's kind of this closed loop of iterating, of improving the simulator, improving the real. And that can help you quite a bit as well in like getting that right.
Thank you. We'll probably have another one question. What time for a
question in the chat?
Was it?
No, there isn't submission of present to the
Ken, are you working on a new version of the Telegarden? Remember, you mentioned something.
Oh, well, thanks for asking that, Damon. Yes, we have been working on something called Alpha Garden, and whereas Telegarden was about human collaboration, tele-robotics, we've been exploring the idea of a fully autonomous garden where there's no human in the loop. And so yes, that's moving a little away from this direction, but I fully expected that would be impossible. But 2 years into it, there's some sense that it actually might be feasible in certain cases. Pruning is the hardest thing, and pruning a plant is, again, something very fundamental. Humans have been doing it for thousands of years, but getting a robot to be able to prune a plant correctly is a big open challenge right now. So it involves deformable materials, basically sequential planning, all the things we've been talking about. And so I'm very interested. I have no idea if we're going to be able to pull that off.
I will keep an eye on that. So thank you so much for you both for taking the time. So one last round of applause for Ken and Ryan.